All right, so thanks for coming to my talk. I hope you guys can hear me. Thank you. So today we'll be talking about sustaining Git performance under heavy workloads and how we're trying to, well, using AI to help us solve this problem. So yeah, let's take a look at that. For those of you that don't know what Gerrit Code Review is, which is the main project that we work on, it's nothing new. It was a tool that was released in 2008 to develop Android and Chrome, and it's mainly supported by Google. It's the only fully Git-based SCM. So what I mean by that is that if you're using something like GitHub or GitLab, the metadata about your code reviews is actually stored in an external database, while in Git while in Gerrit, all of that information is stored in the Git repo itself. And some of the users and the contributors to the project are Google, Qualcomm, SAP, we've got Matthias here, and the Wikimedia Foundation. If you don't know about GerritForge, we're a company deeply committed to open source. Everything we do is open source. We're major contributors to the Gerrit ecosystem, and we help clients globally with the Gerrit installations. This is one of the reasons why we end up finding really interesting use cases and how different companies use Git in different ways, and they all end up with a common problem. That is what we're trying to solve here today. So let's start with what I'll talk about today. So we'll start with what's the problem that we're trying to solve, some Git internal basics that I hope you guys are going to find interesting, the current Git repositories maintenance solutions that are out there and why they're not enough, and how we are employing AI to help us out. So first, I want to start with a statement that I hope it's not too controversial, but SCM, so source code management systems, are the heart of any software company. If your SCM is not working, nobody's working. So it becomes a bit, yeah, it's important that they are performant and up and running at all times. Secondly, I want to say that modern Git SCMs are actually quite reliable. I hope I'm not Jenkins anything, but yeah, you're not going to have really instances where you're struggling with like GitHub or GitLab or Gerrit on a daily basis. What we start to find is that the problem really is more with the Git data itself, and that's what we'll be talking about today. So what happens when your SCM doesn't work, right? It can affect your clone times. So if you have slow clones, it can affect your CI and your CD pipelines, because that's the first step in your CI and your CD. So if a repo that should take a minute to clone starts taking 8, 9, or 10 minutes, then obviously your CI and your CD systems are impacted. You run into additional hardware cost. Obviously, if things are not as optimized as they should be, they're going to take up more resources. And finally, your maintenance teams, so your SRE teams, are going to be running around trying to fix problems and firefighting when really they could be doing more useful stuff. If it gets really bad, then you can even have users that like can push, can pull, and then those developers are not working, right? So you don't really want that. But let's look for a second at what affects the performance of an SCM. So you've got the size of the Git repository. So I don't know how many of you guys have ever tried looking at the size of the history of the Linux repo, which is not that big of a repository. It's 4.7 gigs, which in our world is not that much. But if you look at it, 3.2 of that, 3.2 gigs of that is the history of the repository, right? So 66% almost of that repository is just in the history, and this is not going to slow down over time. This percentage is only ever going to grow over time, right? But that's not the only metric. You've also got the shape of a Git repository. I don't know how many of you have ever run Git sizer on a Git repo, but this is what it gives you. And there's a bunch of metrics here that you can see about this repository in particular, but you can run this on anything you want. And for example, there's a lot of metrics that we want to look at, like the number of ref, if you've got any big blobs, the number of objects, the size of those objects. They're all things that impact how your performance and how your repository is going to perform over time. Another thing that impacts SCMs is the load. So as we go on over time, you're only going to have more and more load on on all of these SCM systems. As you get AI robots adding code review and you're running more builds, the load on the system is only ever going to increase. And finally, current Git maintenance is essentially already outdated by the time it finishes. And I'll dig into this more in a second, but each new push makes the result of the previous GC cycle less and less effective. And also each forced push voids any maintenance action. So we really don't want that. But, and hope you guys find this interesting, what goes on in the Git server? I don't know if any of you have ever asked this question, but let's look at how a repository is structured on disk. So you've got objects that are the core of your repository. And there's 4 types of objects. You've got tags, commits, trees, and blobs. And they're identified by the hash of their content. Okay? So I hope you're all familiar with this. But if you've got tags, tags will reference commits. Commits will reference trees. Trees can then reference. You can think of a tree as like the directory structure of your repo, and then trees can reference other directories, so other trees or blobs. And you can think of the blobs as your files. Each blob is a file. And as I said, they're identified by the hash. We'll see that in a second. So you can store them. You can store these objects in two ways: loose objects, where each file is represented as represents an individual object, or and the name of the file is going to be the hash of the content, right? So if you have ever looked inside your .gif folder, you've got your objects folder, and you're going to see this folders here, 0, 1, 13. This is going to be the first two digits of the hash of the object. And then if you go into that, you're going to see, like, for example, if you go into 01, there's going to be this long file name that nobody really likes, but we can inspect that. That's an object. So if you do git cut file -t, it's going to give us the tree. It's going to give us the type of the object, which is a tree. And if you do a git cut file -p, it's going to give us the content of the object, all right? So we can see that this is a tree, so it has a list of file names, and what is the SHA-1 of the blob, of the latest blob related to the file. The other way of storing objects is pack files. So pack files store multiple objects in a compressed form. So instead of having an object per file, you're going to have multiple objects inside one file. However, each object is not going to know who's who. They need the hand, let's say, identifying themselves. So you do that with an index. An index file is like, it tells you where each object begins and ends inside the pack file. It looks a little bit like this. So you can see we've got two pack files and two index files associated to those pack files. Now, there's also a bitmap file here, which I'll talk into a little bit more detail in a second. Quickly, just to say what a receive pack is. If you're a user pushing to a server, you're uploading pack files. And from a Git point of view, this is called the receive pack because the Git server is receiving data. And then if you're doing UI interactions on Gerrit, you're creating loose objects. Still a receive pack, but now it's loose objects, right? In GitHub and GitLab, this is actually different because the metadata, as I said, is stored externally to the repository. So in those world, UI interactions don't really affect the repository. Conversely, serving Git data is called an upload-pack because if you're doing a fetch or a clone, then the Git server is uploading data to your server. So we call that an upload-pack. But let's look at how an upload-pack works because if you're doing a fetch or a clone, as I said, that's going to be the most important thing, right? So I've given another talk on all of the phases in an upload pack. I'm not going to go in that much detail today, but I'll talk about the first two. So there's the negotiation phase where you've got your wants and you have. So imagine that you've just gone on holiday. You've just come back from holiday, sorry, and you've got your commit A. But obviously in that week that you've been away, your team has been working. So now there's some new commits that you want to push. So your commit A is what you have, and the commit D is what you want. Right. So when you request the latest version of that branch, the server will send the client the latest SHA-1 that it has, and the client responds with a has and a want. Now starts the counting phase. Okay. So you've got commits that need to be traversed to find all objects. So you start with traversing the commits first. So you start from commit D, then you see commit C, commit B, and then you can stop there because you know that the client already has commit A. Now that you've found all of these, you need to still traverse the remainder of the graph. So, a bit painful. And you can imagine how the repository, when it starts scaling, this doesn't scale together with the repository. If you've got thousands of objects and you need to traverse them all the time, it's just not going to scale really well. This gets really even worse when you have clones. Because when you're cloning, you have no halves. So you want the whole repo, and you have to traverse the whole history all the time. So yeah, you need to traverse the whole graph, which is painful, as you see me click through all of this. And again, it only gets worse as time goes by. So what have we done to optimize that? And this is nothing new, by the way. Bitmaps have been around. I think they were introduced in JGit in 2013, and CGit, so GitHub have also picked that up. So they're a great optimization. They're essentially a reachability index of each object. So they help us answer the question, what objects can I reach from this commit. We require 2 bitmaps, one for the halves and one for the ones. So, but you notice here that I haven't put the bitmap on commit C. Why is that? It's because they're generated at GC time. So exactly like Java's GC, there's also Git GC, and that runs every so often. So whenever GC runs, it will generate a bitmap for all the commits that already exist. But obviously, new commits won't have a bitmap until the new GC cycle runs. So the set difference, I'm not going to go into too much detail here, but the set difference of the bitmaps is a really easy way of telling us which commits need to be sent and which objects need to be sent to reconstruct the graph. And you don't need to traverse the whole object. You only need to traverse the objects that have not been GC'd yet. Finally, though, each new push moves our target. So when you do a new push, you create a new object that then needs to be traversed. So until this new commit has been GC'd, it's not going to have a bitmap, and so each new commit makes this situation even worse. So force pushes completely invalidate what we're trying to do and force us to re-go through the whole graph, again making our commits, our clones really slow, and our CI and CD pipelines as a result of that. So the statement that I'm trying to say here is that traditional Git maintenance isn't enough. So we've tried to look at a way to how can we improve this. So first, let's quickly look at what we mean by Git maintenance. I don't know if everybody's familiar with that term, but there's different implementations. JGit and CGit do it slightly differently. I'm not going to go into too many details. But roughly speaking, we compress loose objects and pack files. We generate the bitmaps. We repack the refs. We prune out pack files. We create the commit graph file. We can run geometric repacking, which is a fancy way of repacking only some or only the newest pack files. You can generate multi-pack bitmaps. We don't support these features in JGit, by the way, so Matthias, if you're looking, we want to start doing that. And finally, generating craft pack files too. The general gist of this is that everything has a cost and provides us an improvement. And so we want to try and figure out what's the least thing that we can do that can give us the best improvement. So yeah, this is the question that we're trying to answer. How can we get the best performance in the cheapest way at that point in time? So talking about cheap, why don't we just leave a repo grow unsupervised and just do nothing on it? We can see very quickly that as the number of upload packs increases, the time it takes to execute a receive pack grows exponentially. And very quickly, your repo becomes completely unusable. So nowadays, there's really nothing better than either having some operations, like I was mentioning before, like the Git GC, on a cron job, which, as you can imagine, is really not efficient. And I guess it does the job in most of the cases, but it doesn't scale and there's no smartness to it. You could be overkilling it, you can be underkilling it, you never know, right? So let's look at what happens if you're running your GC on a cron job. You can see here that during the working hours, the number of pack files starts increasing in a quadratic manner. But at some point in the day, and you can guess this is when people start going home and they stop working, the number of pack files starts decreasing. That's because our Git GC is able to recover that, right? It's able to recover that situation. However, this client of ours was lucky because it didn't have a geographically distributed team. They were all geolocated. They would all go home at the same time. So the number of pack files would stop increasing, and then we're able to bring it back down, right? But we don't really want to hope that the people are going to stop working so that we can recover the situation of a Git repository. So we wanted to do something a bit better. And also, let's talk about, obviously, everybody mentions AI. It's a fancy term. So let's talk about why can't a human solve this problem? Well, there's a few reasons. First of all, it's a complex problem space. I've only been talking about a single repository and a single cluster, but you've got companies out there where a single SRE team is going to have to be looking after multiple clusters, maybe even different technologies. You could have the same SRE team looking after Gerrit, GitHub, GitLab all at the same time, and obviously SREs can't know everything all the time, right? So it's complex problem space, and it's also evolving in real time. As I said earlier, with the force pushes, you don't want to have someone there monitoring it all the time, right? So it's just not a really fun job. You've also got different versions of tools, so those come with different versions of Git, different capabilities. You can't know everything all the time. And finally, this is quite niche knowledge. So if the person, maybe you've got one person in the company that knows how to do all of this. If they leave, what are you going to do? Well, nothing good comes of this. So we started exploring AI, and I think that's what you're all here for. So we'll start diving into that a little bit more now. We used an algorithm called reinforcement learning, and we worked on this in collaboration with Shane McIntosh from the University of Waterloo, with which we co-authored, Ponch here, co-authored a white paper that has hopefully is undergoing peer review now and hopefully will be published soon. But how does it work? Essentially, we've got an agent that can act on an environment. We observe this environment to see what state it's in, and we can assess that state, and then based on our session, we can execute actions, where the agent can execute actions. So I know that's a bit of a mouthful, so let's go in order. First of all, let's look at what initial actions our model can take. We've got no action. So if everything is going fine, why would you need to do anything? Just don't do anything. We could create bitmaps. We could repack refs, we could remove keep files, and we could use geometric repacking if you're using a Git server that supports cgit. We had some problems running geometric repacking with jgit, so we're holding off on that for now. If any of you guys have been observant, you'll notice why are we not running full GC as an action of the model? Mainly because it's a long-lasting action. There's other reasons, but the main one is that GitGC can even take 2 hours. So it's hard for the model to know that an action that started 2 hours ago is having an impact now. All of the actions that we run, they need to be quick so that we can have a good correlation between the action that was taken and the state that the environment is in now. So we're not running a full GC as part of the model. Now let's look at how we observe the system. So first of all, we need to think about what we're looking to optimize, because that's going to change the way that we assess success. And if we picked a few random repositories on GerritHub, which is a fairly substantial installation of Gerrit that is open and out there for you guys if you want to use it. And we've noticed that overwhelmingly the operations that are executed the most are the upload packs, so fetches and clones. And that's probably because you've got more bots that are going to be like cloning the repo, running CI/CD, than you're going to have developers pushing new code. So that's what we set out to optimize, how to improve clone and fetch times, and hopefully make them even cheaper. So we need to think about a few metrics that we could use to do this, and we decided against using the clone time because clones can take quite a substantial length of time, and we don't want to wait until a clone is finished until we can say if we improved the state of the system or not. So we looked for operations that we could assess much quicker than that. So one of them is the bitmap index misses, so how many objects are not being hit by the bitmap, and also the number of loose objects and loose refs. Then we need to think about how can we assess the environment, and I already talked about why we don't use time. But how do we compute the rewards? So we used 3 different parts to this. There's the index misses, the search for use, and the action cost. So let's talk about that for a second. This is for index misses, so how many times we're missing the bitmap. If we start from a pre-action state of no bitmap to a post-action state where we have a bitmap, we're going to give the agent a bitmap that is a reward that is proportional to the effectiveness of the bitmap. What does this mean? It means that if we reduce the amount of bitmap index misses close to 0, then that's an effective bitmap, and we're going to give it a full reward. Same line of thought. If we go from a state where we have a bitmap to a state where we still have another bitmap, we're going to give a reward that is none if the rate degrades, small if the rate is unchanged, and a full reward if the rate improves. Finally, we haven't really hard-coded this into the system, so it's impossible. But if we went from a state where we had a bitmap to a state where we didn't have a bitmap, we wouldn't assign it any reward. Then we've got the reward calculation for the search for use. So if you've got a pre-action state, so you need to think of search for use as a scale of time. So what long, medium, and small might mean different things to your company. But if we go from a state where you have on a scale of medium to a scale of, again, medium, we're going to give it a small reward. If we go from a scale of high to a scale of medium, we're going to give it a bit of a bigger reward. And then finally, If we go from a state of high search for a use to a low search for a use, we're going to give the agent a full reward. And then finally, and this maybe is a little bit counterintuitive, but a reward calculation for the cost of the action. So obviously, if you're taking no action, you're going to get a full reward because it costs nothing. If you create the bitmap, it's not an expensive action per se, but it is the most expensive action that we can run at the minute. So we're going to give the agent no reward. And then finally, if we're repacking refs, we're going to give it a small reward because it has a small cost associated to it. And then finally, how does the agent act on the system? So we decided to go with a white box algorithm. There's no fancy neural networks here or anything. It's called Q-learning, and it's quite a simple and explainable starting point. So if we start with a discrete representation of the state of our system, so imagine all of the metrics are essentially boiled down to a bunch of numbers. The past actions, we have a track record of the past actions that we took while we were in that state. And finally, we have a running total reward of the rewards that we received. So we know from being in that state what reward that's going to give us. So how do we select the action that we take? Let's say if we're in state 521, well, we're going to filter out the entries that are not relevant to the state that we're in. We're then going to select the state that we're in and get the action that has the highest cumulative reward. So in this case, it's going to be creating the bitmap. Yeah, and that's it. That's putting it all together. Then the hard job started, and it's evaluating it. So let's look at the theoretical evaluation plan. So we were thinking that by plotting the search for a use over time, if we had no action, and this is what I showed earlier actually, if we had no action, it would spike up and explode quite quickly, really. With a time-based GC, we were hoping that to stay in the game for a bit longer, but then eventually we would also reach a state that we were not able to recover. And then finally, with our agent, we were hoping to keep those levels quite low at all time. So we have two KPIs here. One is the area under the curve. So we want to minimize, if anybody remembers the high school maths, we want to minimize the area under the curve and also minimize the number of catastrophes. Obviously, if we're keeping the clone time low, but it's exploding every 3 clones, we don't want that either, right? So let's see how we went about this, evaluating it in real life. So we created a gym for GHS. So we put our Git server on a bit of a treadmill, sped it up a bit, and actually we submitted a bunch of changes to JGit to improve substantially the performances of it, because essentially what we want to do is be able to load the system and in a few hours generate years of load, and we found that we couldn't do that with the current speed that Git was moving at. So we had to improve it, and we did that quite successfully. We then used Gatling. I don't know if any of you knows about Gatling, but it's a load testing framework that we extended to use with the Git protocol. And finally, we attached the agent to our world, and it was able to read and then consume actions from it. So we called this a warp speed environment. And then finally, we were using it in the real world. So we started with a user. Once we deployed into production, now that our agent is nice and well trained, it knows what to do, we can put it into real world and it will know what needs to be done. What I really like about this is that there's always going to be an element of randomicity. So although it already knows what to do in most of the scenarios, every so often, and you can configure how often, it's going to go off and try and do different things and see if there's any preconceived knowledge that we've inputted that maybe is not the best thing to do. So it's going to go off on a tangent and try and do different things and see how that affects the system. And that's, yeah, the real life speed environment. So if we want to look at what the approach ended up resulting in, we've got our search for a use. So the Node.gc is the blue line, and you can see that pretty quickly this ended up exploding. If we have a GC running every 5 minutes, that's gonna. It was better, but eventually still created quite some problems. And then finally, with our agent that we called Franco, yeah, we could see that the performances were way better than without it. So in terms, this was a 64 to 82 times improvement, which I would take quite often if that was me. So yeah, to recap, Git is crucial to your team's performance. If your SCM is not working, things are not going to be working. The server-side maintenance can have massive impacts on your team ability to deliver in a timely manner. And finally, the time or the threshold-based execution of maintenance is actually far from ideal. So what do we bring with GHS? It's a framework to train an agent who is able to execute different maintenance strategies based on a tailored Git traffic usage pattern. I think that's quite powerful. So essentially, you can plug in your custom actions, so whatever action you need to take, or if you've got a different Git maintenance workflow, you can do that. And you can tune it over real-world traffic. So it can be your traffic, it can be something else if you want that. But yeah, we can train, and we don't even need your Git data. We just need the shape of your Git usage, and we can train the agent for you, or you guys can train it yourselves. And this can be used with any Git SCM. So it can be used with GitHub, GitLab, assuming you're self-hosting them, and Gerrit. So yeah, that's pretty much it. Any questions? 3, 2, 1. I'll take it as a no. Thanks, guys. Appreciate your time.